Okay, so let's start the final talk of this morning session. The speaker is Debargha Banerjee, Professor Debargha Banerjee. He will talk about Ribet's conjecture for Eisenstein Maximal ideals of cubic free level. So please start.
Thank you very much for the introduction, and thank you to the organizer for giving me an opportunity to speak. It's always a pleasure to speak here in ICTS. So as I'm speaking on this Ramanujan hall, so it is better to start with the motivation from Ramanujan. So this motivation of this work goes back to Ramanujan. So you have this delta Q times 1, 4, this is 1, n, and tau n, and 11 mod 691. Okay, so what you have is that this is Ramanujan's congruences, and nowadays we don't do this. I mean, it's almost 100 years. So now what you do is that what we tell is that delta is a cos forms of level 1 with 12 and E12 is Eisenstein series of level 1 and with 12, and I have a congruences between delta is coming to mod 1691. Okay, and the motivation is I want to do it instead of this level 1, I want to change to the general level. So how far this general level you can go, and I will give at the end, I will give some congruences similar to this. Okay, let's go slowly. So you have this congruent subgroup, naught of n is contained in cell 2z, and this gamma naught of n acts on the upper half plane. So you have modular forms, and you have this y naught of n upper half plane. This is a Riemann surface. Unfortunately, this is not compact. You compactify it by adding the cusps in. So this is cusp, and for me, I would like to see the space of modular forms to gamma naught of n as holomorphic sections on this curve. Sorry, yeah, sure. Okay, and 2 of naught of n, it's 2 of n. You have this naught of n also. You have this. This is a space of Eisenstein series. Yes. So it's similar to what you have here. So we have one side you have cusp forms, and one side you have this Eisenstein series, and I'm interested to how to get this number 691. Okay, so this is if you take this the way dimensionments, if you do that, so if you do that, this is just fz dz, and corresponding to that, if you E Eisenstein series, Ez dz, the corresponding differential forms, Ez dz is holomorphic on y naught of n, but it has poles. Unfortunately, it's on naught of n. Okay, and on this space you have the very important operators, Hecke operators, acts on this. Okay, so we can talk about Jacobian. Not of n. This is still over C. 0 is 2. Hat below H1. It's not of n. Z. And how do you see this H naught? You have this beta. So this is the dual of the space of modular forms, and alpha beta, that's going to take this F to the periods beta, the dz. That's how this guy is a subset of this. And I would like to, so with a classical theorem, model well, that's going to tell you that this is in K or so maybe this conference we are more interested in R, but I'm interested in this torsion part. And I'll give a recipe of what is for general n, what is your J naught of n K tor. And so remark, so K will be determined, I did not specify this K, but K will be determined by n. Okay, so I will give you this. So you have this D naught, naught of n. This is your D. X, where this X belongs to partial of X naught of n. And inside this, you have this P naught of n is D to naught of n, D is divisor of F belongs to C of naught of n. And what this cuspidal subgroups is defined to be the ratio naught of n inside this pic naught. Okay, and it's yeah. Sorry, yeah, I should do it. Sorry, thanks. Yeah, that's why. And so what is the connection with this board and that board? So connection is established by old theorem, Manin Drinfeld. Drinfeld implies this Cn in J naught of n. So I'm not specifying this. There is a reason. What is this K? Not specifying it. So Cn is contained in J naught of n. That's fine. But this tor part, I mean, sits inside tor part is this is the Manin-Drinfeld theorem. Okay. So now, so the question is how far this Cn from this J naught of nk tor. Okay. No, that is the whole point. X naught n is defined over Q. Yeah, but when you're taking this K, X naught is of course there is a model over Q. No, that's not. That is the whole point. Yeah, certain assumption definitely it's true. That's the next thing. Okay. So it's a classical theorem. It is Oak's conjecture, and it's been proved. This is Mazur's theorem. This influential 1977 paper, ICTS paper. No, I will come to it. Just wait. So if you take n to be prime, then what first is J naught of P, what he is saying, Mr. Rajan is saying is correct. Okay, so this is actually cusps are all defined over Q because there is only two cusps, 0 and infinity, and actually Cp is equals to J naught of PQ torch. And he computed this order also is J naught of PQ dot. This is your NZ, and this N is a numerator of P minus 1 by 12. And if you look at carefully, if some of you are familiar with Eisenstein series, this is a constant term of the Eisenstein series. Okay, and this is the order of P mod M. M is certain maximal ideal. I'll define ideal of P, and this is the Eisenstein maximal ideal actually. I'll define this thing. And this is the starting point of this walk. Okay, and the question is, what can you say about general N? Okay, so definition, ideal N said to be Eisenstein is like what you expect. Eisenstein is the two-dimensional Galois representation, semi-simple Galois representation, rho m from GQ GL to P mod m is reducible. Of course, this two-dimensional, there is not much choice, and this rho m is basically alpha m, Edixhoren, beta m. Okay, and so this Galois representation is you can wrote down this all the properties that is similar to Diamond Schumann. Last chapter of Diamond Schumann, where he wrote down for irreducible Galois representation. So it has a similar property like this, and this is determined by this is two-dimensional Galois representation. It is determined by the trace and the determinant. So you have this properties rho m. This is rho m. Right. Side. Then, so this is going to give you this L. You have this P mod M sits inside Z mod LZ. So this is your bar. So this is going to give you L. So this is rho m is unramified outside Ln, and characteristic P does not divide Ln. Rho m of P satisfy this usual square P plus P. Most of the time we study this irreducible, but this uses Deline's theorem, and that's true for any eigenforms. Okay, so I'll just briefly recall. So what is the how the Mazur's proof of this Oakes conjecture goes? So So as I said that if you take n to be prime, so the Eisenstein series is better. It has only one Eisenstein series, and you can look at this Hecke eigenform, Hecke eigenvalues for this Eisenstein series. Key points in Mazur's theorem. Okay, so you have only one Eisenstein series, so we can talk about this ideal, not of n. This is your one. Let's not divide n. And what you have that up minus.
Excuse me.
Yeah.
What was the precise definition of T? So it is subalgebra.
T is a
end
subalgebra
of Z or something.
for all p.
Whole
When p
P.
dividing n also it's allowed.
Yeah, end of.
Yeah, endomorphism is Jacobian.
Of Jacobian. Okay.
Yeah. So you have this up minus 1 that belongs to I naught of n. And what he has proved is that you start with an arbitrary maximal ideal M, then this M contains I naught of n. And of course, this is maximal, so we better be M. You have M equals to L times naught of n. And those L's are those that divide this Z mod nz that I put down there in this. Basically, this constant terms of the Eisenstein series. Yeah, so it's not constant term, but something to do with constant term. Yeah. Sorry, I naught of n. This is, you take it as a definition. So this is subset of Tn. Yeah, that was you. T. Okay, so maybe this T. This is Tp, and this is better. Yeah, and P does not divide away from P. Okay, so no, I should not call it P because this. Yeah, it's better I stick to Tr because sorry, there is a prime. I'm just recalling Mazur, so Mazur's I'm taking n to be prime. Okay, so yeah, and then P is the level. So now it is P is n. So EP minus 1 is this. Okay, so the second step is this I naught of n, and here let's this J naught of n, both this tau and hospital subgroup, and three. So I already wrote down this 3. So we have this Tn modulo this, yeah, I naught of n. Yeah, so it's isomorphic to Z mod nz. And as a corollary of this, what we do is, in particular, just says that for unique maximal ideal, Cn of m is non-zero. So you take this part of the cuspidal group where it is m part, this is annihilated by m, and this is non-zero. And for this is 1977. In the last 45 years, there is people thought about it, how to generalize it, and the main point is that if you take n equals to p, there is lots of advantage things happen. If n is square free, you have a nice model, and moment you have all the powers p dividing n, so there is no nice semi-stable model. Even for p square dividing n, there is not there. At the end of this paper, IH's paper, Dylan Rappaport has a model, but this kind of model is not there if you take higher powers of p dividing n. Okay. So so for general n, so Ribet, Ken Ribet, n. So Ribet conjecture that says that if you take any Eisenstein maximal ideal, for all maximal ideal M. So you have this Cn of M. This is non-zero. And the reference for this is his student Hajong Yeo's paper, I think this is 2016 Israel Journal of Maths. And he made this conjecture that the Cn of M is non-zero for all n. Okay. And in this paper, he has proved it, you proved it, proved the same for n square free. Okay, and I will just tell that how this n square free is again little that is okay, because you have nice models exist. So x naught of n, you have nice model exist. So I will just in this board I write down the what more it is needed to prove this conjecture. This is the Ribet's conjecture that says that if you take any arbitrary n and if you take arbitrary maximal ideal M, then the Cn of n is non-zero. Okay, and so I'll just go how you proved it. So this is Yo's proof. So what you have? M. So this is same as I naught of n. And only the P dividing n is dividing n, P M, and UQ minus Q is Q dividing n by M. And what he has proved is the following: Tn I and n, this is isomorphic to Z mod nz, where this n is some carefully chosen divisor inside Cn. Okay, and he went on. Yeah, I should keep this. To compute this up to the order of power of 2 and 3, so d is same as square root of phi n 24, and psi n is 1. In the same way, this imn annihilates this Cn. Okay, so I will just so here what is the advantage of this n square free? So what our work is that we generalize it for general n, in particular p square dividing n and p cube dividing n, cube free. Okay, so p square dividing n and any 2 power dividing n, we generalize this Ribet's this Yo's result. Okay, so any questions? Sorry? Yeah. Yeah. What is this? Sorry? N is this order. Yeah. N square, here for you it is n square free. So now we are proceeding to arbitrary. M is the divisor of n. So you can play around with this n. Yeah. There are different choices for arbitrary n, there are different choices. Okay, so why you looked at this n square free? So for square free, you have certain advantage. Namely, There are two advantages. In okay, so one is starting is just a Galois representation, reducible Galois representation. This is one direct sum chi L bar. So there is no character involved in this reducible Galois representation. If you take the n to be square free, so L chi L character. I put this chi L bar. So in general, if you take the arbitrary n, general, so rho m bar will be just alpha direct sum phi inverse of chi L bar. So, but if you take n square free, then rho m is always of this form. So there is no character to worry about. So that's an advantage of working with n square free. Okay. And the second advantage, as Rajan has already said, all the cusps of x naught of n are still defined over Q. So I will just tell a bit about. So the model is defined over Q, but I need to we need to ensure that all the cusps are also defined over Q. I will tell you what is the meaning of this. All the cusps are defined over Q. So this. So this is the Shimura's notation of cusps. So you have this, as I told you, these cusps are defined over Q. This is alpha beta belongs to Q, and this alpha and beta, this so a priori, so you have this alpha beta. This is defined over is Shimura's notation. This is this, and this Galois group. So this Q zeta n over Q acts on this cusp by this acts on this AB gamma by sigma r gamma equals to A R inverse of B. So there is an action of the Galois group on this cusp. Okay, and this sigma r is the zeta n equals to zeta n to the power r. The GCD of Rn equals to 1. Okay, so in particular, that just shows that if you n to be non-square free, then there p square dividing n. I'll just write down. In particular, this is going to tell you. So, so we followed this Glenn Stevens paper, transaction paper, but it is well known in the literature. Okay, so in particular, that just says that if you take any arbitrary cusps of this B gamma, this is defined over Q zeta T. So cyclotomic field where T is GCD of B comma N T, and I am supposed to define D, and D is GCD of Bn. So it is in general not defined over Q. In particular, just shows that if you take this p square divide n, then this 1 by p of gamma is Q zeta p rational. Okay. So we need some. So we need to rectify these two things. One is the character now there. So we need to have certain control on this character alpha. And the second, now unfortunately, these cusps are not defined over Q. So we have to do base change and something to prove this conjecture. Okay. Okay. So now I just first step, I would like to see how to control get some control on this alpha. Okay, so that's my first step. And the second step, I will just see that how we can control this Q subatomic thing. Okay. Okay. So any questions? Okay. So the tackle the first thing. So, so it was there in the more or less in the literature. So this is okay. So you take this M is Eisenstein. So I just put this assumption n equals to n1 square n2, where n1 n2 square free. N1 n2 square free. M Eisenstein Maximal ideal. Ideal if and only if there exists character epsilon bar from GQ to Km star. Okay, so so there is this is one thing that's a certain advantage over Q, because always is FP, but here we are not in this position, so we need to fix an isomorphism between these Km Q mod M inside this FL bar. So I'm starting with the maximal ideal M. So that is the only information we have. Okay, so unramified, this is the crux of this proposition, right? Outside N1 such that rho M bar epsilon M bar inverse of phi M. So this is inverse to each other because we are in the gamma naught case. In general, there is going to be two character. Yes, but the main point is that I want to have some control on this character. Okay, so I just write a few lines about this proof. So I just tell you that it looks like a reducible. Of course, it corresponds to the Eisenstein series, but it is mod P Eisenstein series, and it is not an unique lift to a characteristic zero Eisenstein series. That is the challenge. So there are lots of lift. I am never saying this is a mod P Galois representation. It should reducible Galois representation. It should correspond to an Eisenstein series, and the lifting will be there is not a well-defined lifting. This is the N, and there is an Eisenstein series for that. So that is the challenge here. Yeah. Okay, so I'll just say a few lines about the proof. Proof. So remember, we are assuming this rho M is alpha M bar. M bar. So any character I bar from GQ to Km star, we can put this of the form theta bar chi L to the power I, but theta unramified at L. Okay, so then for this Galois representation, there exist cos forms. Fm belongs to naught of n Am. So this is result due to Ribet, and Hida also, he is not here, but Hida uses thing, but it is well known. If you take this, there exists a Fm there, and you can compute model Galois representation to that, and it's an old paper due to Edixhoren on weights of weights in series conjecture. So it just says that what exactly is the shape of this GL, and this will be A of AL inverse. This is AL. So if you have L does not divide into, this is basically Derin's thing, and if L divide into, so you have there exist GM one level lowering kind of thing, EM, such that, so this part is Fontaine's thing. So you have this lambda L bar K star 0 of AL. Lambda is a character, the unramified character that's going to take this lambda prop P. Lambda of X, character that takes prob L to X. So we do a little bit of computation, and that's going to give you this proposition. So now we have control on this on N. Okay, so you have this epsilon M, you have certain control on that. So now we have to proceed to how we can just get some control on this on this Q. Okay, so just proceed theorem. So just so our theorem says the following. If you take N to be Q free, M Eisenstein maximal ideal, with residue characteristic okay, so characteristic of this mod M, this M, and I have certain assumption L6N1, so whatever this, I don't want to talk about this. So this, then Cn of M is non-zero, and we can pinpoint what are those n's for which this is non-zero. So that is our theorem. So I'll just proceed to a proof of this theorem. So any questions? Okay, so so the key idea of this proof is the following. Idea. Okay, so find analog of law of IMN. So the second thing is to replace this cuspidal subgroup CMN with the subgroup with associated to Eisenstein series by, because I'll define how we can associate to an Eisenstein series CE Eisenstein series E, and this is an idea goes back to Stevens, and then you do appropriate base change. Okay, so and do appropriate. Okay, so I'll just talk about what exactly is this Eisenstein series associated to. Okay, so okay, so I'll define this group. Okay, so he has defined here. So this here. So this C, we have the Eisenstein series E. Series. As I told you, so you have this E has poles on the boundary. Okay, and let's take this RA, RE. This is a free abelian group. Generated by the residues. In particular, what I'm saying here, that you have this E here, Eisenstein series, you associate to it delta of E. This is your summation over X, A naught of E over X times X. So now X belongs to boundary of X naught of N. So now this is a free abelian group, and inside this is not a finite group. It's a for every cost there is a contribution. So this A naughts may not be now defined over Q. So okay, and then you have this P, the abelian group. Generated by periods. Of series. So what is true is that this PE, so this is of the form, these periods are of the form Z0 to gamma Z0, Ez dz. So what is true is that this PE is contained in RE. And the Stevens that work in 1985 that shows that there is a copy of this group RE or PE inside this CN. Okay, and if you start with an arbitrary maximal ideal, this is going to give you an Eisenstein series there in the cuspidal subgroup, and that is going to give you that Cn of M that coincide with this cuspidal subgroups. And what we did is that we computed this order of this cuspidal subgroup. That is going to give an analog of this Z mod NZ. Okay, so so before proceeding with the proof, I will started my talk with Ramanujan congruences. So I will just give some examples of how we can talk about the similar to this. Okay, so from the beginning, so I am just not square free, but cube free. So if you take these examples, if you take n to be 121, and if you take a phi quadratic character, inductive phi equals to 11. So here in our paper we use this certain nice Eisenstein series. This is not Diamond-Schulman's Eisenstein series. This is an Eisenstein series that goes back to Andrew Wells's paper on totally real field, and it's being used here. So you have this. So I need certain thing about L function and Hecke eigenvalues. So that's box for here only for this Eisenstein series u to the power n. So if you compute this analog using this, what you have this is 55 so minus 11, and nowadays I went back to the L function and modulo form database. So there is actually a modulo forms f what is known as 121.a.d that belongs to 2 naught of 121. And what we realize is that E phi z is congruent to fz mod 11. Okay. And one more example. So this beta phi is something coming from this, once you compute this CE, so there is certain numbers, order of this CE for n give free is going to give you that number. And there this 5 divides. 5 divides this number, sorry, maybe I'm not, this is mod 5, that is, yeah, mod 5, yeah, sorry, this is mod 5. So this 5, this number, and so there is a congruence between Eisenstein series and this cusp forms. So one more examples. So if you take as examples 2, you take n to the p square 2 times 13 is you have primes there. This is 4. So what you do is that so there are 5 new forms. And this one of them is dot E, and if you can see that there are examples, so indeed you have this E phi, so it's 13 just is going to be dot E mod 2 actually. Okay, so so while doing this computation, we found a very nice thing. So I'll just state it before doing this example. If you take the to be n is p square n prime. And if you take this phi of m, and this is congruent to p mod p, and I have an explicit recipe to how to do this p, and this modular forms of a 2 not of n, this correspond to an elliptic curves EF, and it turned out that this, let's say p divides q. Q is the only prime isogeny other than 2, 3p. So this is what we so we are doing it from L function model of database. We're doing all these congruences. This happens, and with that there is we do not have any proof of why it is true, but there is with this numerical examples we get these congruences. Okay, so now I just in a last few minutes I will just give I suppose I did not define this E phi of m, and this is any questions? Yeah, mod 2, yeah. Okay, so so while doing this n arbitrary n, what you have to do is that you have a good control on an Eisenstein series, and you take this critical refinement. So we are starting with the Eisenstein series E phi, so gamma naught of f square, and you have this gamma L. This is your 1, where L does not divide f, and if you take this G belongs to M2 naught of square, so then L phi Gz equals to Gz phi L G of Lz. So this is critical, and L phi minus Gz equals to Gz L bar of Lz. This is ordinary, and if you do, so I want to get a basis of all the Eisenstein series. So basically n cube free is a natural question. Why you're looking at this n cube free? Because if it is n is not cube free, then there is an old result due to Edixhoren and Coleman that says that it is going to be not going to be semi-simple. So we need this Hecke algebra to be semi-simple. So that's why we need this n to be cube free. Okay, so now with that, we have TR of phi of m. Yeah. Yeah, so I'll just so we need so you see for when I'm doing it for n equals to prime, so I told that EP minus 1 belongs to m. Okay, so I need the information that Eisenstein series is semi-simple for all primes, not for p dividing n, does not divide n. So p does not divide n, of course you can find it, but all this action is happening for p dividing n. So we need an Eisenstein series, and so we need to pinpoint an Eisenstein series. Okay, so if, but there is an old result due to Edixhoren and Coleman that says that if you take cube dividing n, then this Hecke operator, this whole Hecke algebra is not semi-simple. So we cannot run this process with, we need this with this critical and ordinary refinement. I want to get an Eisenstein series, and which is going to be semi-simple. Okay, yeah. Sorry? Yeah. No, not infinite only. Yeah, yeah. So, but then for general M, I don't know. So there is a possibility it is not semi-simple, right? Yeah. So in that case, we found out the examples of that's the next thing I'm going to write down. So there are examples. This Eisenstein series is we have a basis. So we need to write down this basis as a Diamond-Schumann basis is not going to work, because that Eisenstein series is UP operators are not nice. Okay. So it's so we need to find a new basis, and there if you p divides square divides n, then there exists a basis of Eisenstein series which is going to be a nice eigenform. That's what we are using. That did you answer my question? Your question? Yeah. Yeah. So yeah. So definitely for cube free there are examples. So we cannot proceed with that. So that's why we have to put this assumption. Yeah. Okay. So this TR of this is E phi of s. So this is an operator. This is going to be okay. So this is E phi of m. So phi of m. So this is E phi. This is critical at q. So q heading m, and ordinary at t dividing n by n. So this is my notation, and then you have this phi r plus phi bar of r E phi of m, and I have information about this p dividing, and also you have this uq E phi of m equals to phi bar of q times q E phi of m, and ut of E phi of m equals to pt E phi of m prime by m, and up of phi of m. So this is going to be an eigenform of all these AK operator. And what we realize that if you take n to be cube free, then we have an analog of this Mazur's theorem that says that if you start with the arbitrary maximal ideal, we can write down in this form again for n cube free, so this m is L times this. This is just an analog of this Mazur's theorem. Yeah. Okay, I'll stop now.
Thank you very much. So are there any questions or comments? So, okay.
Hello. What stops you from going a bit higher, like cube free or something?
Yeah, that's what it is. I mean, this, I don't know, this is semi-simple. So this process, I don't know if for every m you can get a
Eisenstein series.
Eisenstein. For p does not divide in, it's not a problem. But so okay, so Eisenstein ideal paper means that Eisenstein ideal should maximal ideal should correspond to the Eisenstein. This correspondence, maximal Eisenstein maximal ideal corresponding to Eisenstein series, that depends information for p dividing n. And I don't think that's this Hecke algebra is not semi-simple. So
Thanks.
Are there any other questions or comments? Okay, so let's thank the speaker again.
okay.